So about half of the worksheet today we will be doing Spark streaming. So the problem with Spark streaming is we can only have one streaming job running in a given cluster, right? So I'll mostly be doing it in actually a sandbox cluster here, just to make sure nobody else can log into it. But those of you who are in the usual cluster, so without a community presence, I cannot get you community edition either, right? So this is also, and if all of you or the observing students had the community edition of Databricks, then we can all be doing streaming individually, because each one will have your own cluster. Okay. So let's try to get the community edition for the observing students maybe before the last lab next week. So the last lab lecture is before the 3-week break. So the hope is that you would have had enough coverage of various aspects of Spark to be able to think more, seriously about what project you want to do. Right? So that's the plan. So today's topic is basically Spark streaming, which is, remember, the third major component of the badass substack, which is Apache Spark. Right? So in streaming, the third part, so remember the first one was data frames and Spark SQL, which allowed us to interactively query data and so on. And the second one is basically machine learning library. So we're seeing various parts of the MLlib. And then finally, this one is Spark streaming. Zoom cloud meeting. This one will be lost. Okay. I'm going to assume the recording is happening. Continue. So if you go to week 6, we have folder 12 and folder 13. So in week 5, we sort of didn't quite get to the end of this power plant pipeline, because there's quite a lot of concepts. So we will go back and revisit it again in the end. And the tuning and evaluation, sort of we only saw parts of it. And then the last step, deployment, is going to essentially ask you, have you use Spark streaming. So the idea is that we train this model for this regression problem, and then the model essentially is compared with linear regression, multivariate linear regression, and then we compare it with the decision tree, and then we compare it with gradient boosted trees, which are essentially ensemble method, where you're not just using one decision tree, but multiple decision trees, and somehow learning from all of them. And what we found was that the gradient boosted regression trees were significantly better in terms of root mean squared error than the best performing linear regression model. So again, best performing means we tuned and did cross-validation over the hyperparameters. Right? So now in deployment, what we will be doing is essentially take this learned model, have it sort of sit there, and then somebody is querying this learned model for here are my environmental variables or my features. Now what is going to be the predicted power output? So this sort of query is coming at you, and the model that has been trained and tuned is now deployed to serve predictions. That's the last step. Okay. So we'll come back to this. So what I have here in week 6 is essentially the full-blown version of this. So this has all of the steps and sort of coming attraction. So here's essentially where we're going to be doing deployments. Okay, so before we do that, we have to understand Spark streaming. So let's get into Spark streaming. So I'm not going to work from here. So I think if you see there is class cluster 1, enroll students and observing students. So essentially, for a given cluster, there can only be one streaming Spark context. So it can be at most 3 people working, okay? So maybe you just want to follow it, or so then you can sort of do it later. And hopefully by next week, all the observing students will have a Databricks Community Edition, and then we can, you can basically have your own cluster and try stuff on your own. Okay, what is Spark streaming? So the idea is that we want to be able to do scalable, high throughput, fault tolerant stream processing. Okay, so we have some sort of live data streams. So the running example for the next 2 notebooks is actually Twitter. So we're going to plug into Twitter Firehose and essentially monitor tweets live as they're coming out, right, over the whole planet. And that's a very nice example of a stream, and it's quite a lot. So we're looking at every second, every tweet. So there's about 40 to 70 tweets happening on average, for example. And then we want to do something with each of these tweets, and there's quite a lot of information in each tweet. So we will sort of see that. And of course, the general problem is you have information that's coming at you. Could be query information or whatnot, and then you want to essentially somehow process this, right, in a fault-tolerant and scalable way. So this particular intro is basically a remix of the Databricks guide right here, and then the parts of the streaming programming guide. So those of you who sort of have more industry experience, the idea is that we want data to be ingested from multiple sources, right? So links to these are, you can look at it, Kafka, Flume. For us, we'll mostly focus on Twitter streaming API. And we'll make a little example with sockets as well. So here's the sort of big picture. Spark streaming allows you to ingest data from multiple sources and basically put it back in either a distributed file system or in some other database, OSQL database typically, or on a dashboard, so you can sort of display something that's been processed from the stream. So internally, what's going on? This is the idea. So you have input data that's coming in. Spark streaming basically breaks it into batches of input data, and each batch gets processed by the Spark engine. So engine basically means sort of core of Spark or MLlib or Spark SQL. So these things can be used to process the batches of data, and the batches of processed data basically come out. That's the big picture. So of course we can do transformations and actions that we can do on REDs, because the way the batches of input data are broken up are through these things called D streams or discretized streams. So a D stream is nothing but a representation of a sequence of resilient distributed data sets. So the usual RDDs, except now we have a whole sequence of them. So each one is going to be an RDD, or a discrete stream. So of course, we're going to focus on Scala here. I don't think these streams quite exist for R yet. And this is part of the reason why we're sticking to Scala, so we can use all the nice things we want. Could the person on the other side please mute their microphone? Thanks. Okay, so here are various resources. So the Spark streaming programming guide is the best place to start. There are some links to Databricks worksheet on notebooks on debugging, and this is very important. I spent several hours yesterday wasted because I didn't read the frequently asked questions. So one of the main things is that we cannot have multiple Spark streaming contexts in the same cluster. Okay. So let's sort of get our hands dirty quickly through examples, okay? So we sort of have a working idea of streaming. So the first thing we'll be doing is screening word count. Okay, this is maybe conceptually the easiest, but we have to sort of abstract away how the underlying streams are created. We don't need to really understand how these random sentences are being created. But from there, we will essentially do the standard word count we did on RDDs on our week 2.1. But now these streams. Could you please mute your microphone? Is it Roger on the other end? Is that Roger? CNWRAJ1? So I don't know. Roger. All right, well, I don't know. Just have to ignore them, I guess. Okay, so there are other examples, Kinesis and some other Python examples. These are just Databricks notebooks, so you can chase them if you want. We're mostly going to be restricted to the streaming word count and the Twitters. So first what we're going to do is just get some configuration set up. Okay. Maybe I'll go get Paul before he goes home, or maybe he's on. I'm not sure. Someone call Roger and ask him to maybe turn off the CNWRAJ1. Sorry. Siva, do you want to just take over? Let me go get Paul, okay? Because I won't be able to teach. It's going to be constantly annoying me. So it's already connected to a streaming cluster in the sandbox.
I'll just give some background information on Spark streaming. So Spark streaming is not actually a streaming. It does micro batching, meaning it's not a real-time streaming engine. You cannot compare it with other streaming frameworks like, say, Apache Storm. So what Storm does, for instance, is each data point that you receive, it processes that at that point of time itself. So Spark streaming is not a real-time stream processing engine. It's a micro batch real-time processing engine. So it's a near real-time processing. So what you see here, you can see there's a variable called batch interval seconds. What this variable does, like we have created this variable for our internal use, but what it actually does is it controls the size of each micro batch. What it means is, let's say you get number of tweets per second, let's say from 50 or 60 tweets per second. When you say the batch interval is 1 second, all those 50 or 60 tweets together will form one little batch. Right, so your D stream will contain one RDD with all these tweets. So if your batch interval is say 5 seconds, it will have 5 RDDs each RDD will contain all tweets that have been received for 1 second. And that's how it, and once you get the stream with all these tweets, let's say, you actually do a batch processing on top of that. Okay. And just like a Spark context is a starting point for a Spark job, Spark streaming context is the starting point for a Spark streaming job. So the first thing you need to do is set up a Spark streaming context. And for setting up the Spark streaming context, we have it's part of the Spark streaming package. So what we do is we just import these packages. And like Ras was explaining about D streams are the basic abstraction in Spark streaming. Just like RDD is an abstraction for Spark context, the D stream is an abstraction that's used for Spark streaming. And a D stream, like I was just saying, it actually contains multiple RDDs. Like you see here, we have 4 RDDs, and these RDDs contain data that's received during this time interval, like 0 to 1, 1 to 2, and so on. So in this example, what we are doing is we are setting up something called a streaming receiver. So streaming receiver is like the front end, or so you have streaming data. It is received by a streaming receiver and is made available to the Spark streaming context. So if you want to connect to some other streaming source, like we have a few streaming sources here. Kafka, Flume, Kinesis. Let's say you want to connect to some other streaming source, maybe say RabbitMQ or Redis or any other streaming server. What you need to do is you need to write your own stream receiver, or other people have done it for you, so you can just reuse them. And what the streaming receiver does is it has a certain life cycle. So when the Spark streaming context starts, it actually calls the onStart method of your streaming receiver. When you're stopping it, it calls the onStop. And during the time it is receiving tweets, it calls the receive method each time a tweet is received. So what we are doing here is just setting up a dummy stream, and we are mocking the data that is generated. So what we are saying is when Spark streaming receiver starts, you start a Java thread, and all the thread does is it generates some random integer between 0 and 9, and it makes that integer or this particular entire message available to the Spark streaming context. So having this receiver separates the data source from the processing part. So you can connect to any data source, and then it is available to Spark streaming for processing. So I'll just run this streaming receiver. Yeah, and the streaming receiver is running, meaning your data is being generated right now, and we are generating it using this particular statement, right? So when you call store, what it actually does is the store is a method in this particular class receiver, and it is taking the string and storing that string into the receiver to make it available to the Spark streaming context, right? As you'll see in this example. So here what we are doing is creating a Spark streaming context, and the Spark streaming context needs the Spark context, and you also specify this second parameter, which is the duration for which you want to batch your streaming request. So it could be as low as 0.5 seconds. So Spark streaming supports batching from 0.5 seconds up to hours together. You can put hours. It cannot be lower than 0.5 seconds. That's why it's not real time. It's near real time, right? And once you create a Spark streaming context, the next thing you need to do is create this receiver stream. So this is where you're hooking your Spark streaming context to the source from which you receive your data. So if it's Kafka or Kinesis, you specify that here, and you specify the settings for your let's say, Kafka streaming server, saying that this is where my zookeeper is, this is the port on which you need to listen to, this is the queue on which you need to listen. But since we are using a dummy source, you just say dummy source. And if you see here, the dummy source is taking a rates per second as an input parameter just to control the number of messages that get generated. And we are passing that here. And this variable, as you see, was defined earlier, events per second, right? Yeah. So what we are doing is we are hooking our Spark streaming context to the receiver, and that will give us a discretized stream. So dstream is nothing but a sequence of RDDs. And the dstream also defines transformations and actions. And one of the transformations is a flat map. This is similar to the flat map that we have in RDDs. And what we are doing here is the lines that we receive from the dummy source, we are splitting them by the space. This is really similar to the example we saw on day 1 or day 2, where we are splitting the lines from the text file by spaces and then assigning a count of 1 to each word and then grouping them. So it's the same thing, but instead of doing it on RDDs, we are doing it on a dstream. So these are methods on dstreams. These are redefined again. Right? And what they actually do is they're just wrappers around RDDs, transformations, and actions. So they'll go in and call those for us. So we are we are doing a flat map on the stream. And then for each word, we are mapping it to a tuple with the word and a count as 1. And then we do a reduce by key. So words with the same words are grouped together and reduced, and we get a count of the number of the words. This particular method for each RDD is unique to the dstream because the dstream contains a number of RDDs, so we are looping through each of the RDDs, and for each RDD we are converting that to this particular data frame and registering that as a table. Right? The reason we are doing this is just to query the stream at real time, and you will see how the counts of the words change in real time. Right? We'll see that example. And then we are just printing these messages. Yes.
The dummy source, it's not extending. So, is there any receiver class?
Yeah. It is. So the dummy source is extending receiver. So all of these steps are actually steps to set up your Spark streaming job. Once the Spark streaming job is set up, you need to call Spark streaming context.start or remember. So this will actually start your Spark streaming context. And then you need to call Spark streaming context.stop. But we are not doing that here because in Databricks, you have a helper method to get a reference to the active Spark streaming context. So we'll see that part of code again. So just run this now. Okay. So I think this particular function is not called, it's just defined now. Maybe later on we'll be calling that. Anyway, so this is what I was explaining, how the lines are being transformed to words, and then we are counting the words. Yeah, so these particular statements are the ones that help us get an active context, Spark streaming context for a Databricks. So these methods are not available in Spark API. So only if you're using Databricks, you'll get this this helper function.
Is this a count? This is a batch word count table.
Mhm.
Is that will be refreshed for each coming string?
Yes.
But
Yeah.
it's not aggregated to count.
No, it's, yeah.
It's per string long, basically, per each string.
It's counted within each RDB.
Yeah. So you can see here, this is where we are calling start. So this is when the Spark streaming context will actually start. And then you need to call this method await termination. There's also another flavor to it, which is await termination or timeout. What that means is, if there's no data received for this particular interval, it'll time out and it'll stop. Okay. So this is okay, it's still running, and you can see that our dummy source receiver we defined earlier. It had these statements for each number, and you can see that the data is being received by the Spark streaming context. Right? And these event count is this one. So you're counting the number of lines in each of the RDD, right? So that's what, and we are just taking the top 10 just to make sure some data. Okay, so let's see the interactive querying. So we saw that we registered each RDD as a temporary table. Yeah. So you can see that for number 4, which is treated as a word, the count is now 84, and if I run it again, it's 92. So each time this particular table is being refreshed, so each time you run the query, it's interactively going to the Spark streaming table, the table that we registered, and it is bringing the count for us. Right? So it's changing every time. So you can. So what you can do is you can set up a query like this, and this can be served on a dashboard. So you can see a streaming dashboard. Right? So you can see a streaming dashboard of different word counts and how they are changing. So you can possibly set up a loop that runs every second, let's say, and run the same query and take the output and hook it to a dashboard, and you can see the dashboard changing live, the counts changing live. Right? So that's the power of Spark streaming.
So before you stop, can you show the cluster user UI for the streaming? So
yeah, okay.
So you need to open cluster.
This one.
Yeah. Just hit the streaming tab on the top right. Yeah. This sort of shows you the streaming rate, number of events per second coming at it. So the streaming job is currently running random int. You can go back and stop the job.
So the big stream value was 1 second.
Right now we have set the interval to 1 second, but you can set it to whatever time.
There is one statement called SSC.remember minutes. Can you
Yeah.
It is to remember.
Okay, so then if you go back to the UI, you'll see that the streaming job has, I have to go up slowly. So if you hit the streaming tab again, it will disappear. Okay, so if you don't know that you can only have one streaming job running, crazy things can happen. So this is a good way to just make sure that there are no streaming jobs running in the cluster in case you want to play around and And of course, you can kill other people's streaming jobs, I believe.
So this is something to do with Databricks. Like in Databricks, for each cluster, you can have only one streaming job. If you're running it on your own cluster, for each JVM, you can have one streaming job. Okay, so that's something to keep in mind. So what that means is if you have 5 worker nodes and 1 driver node, you can have 5 streaming jobs. And each time a streaming job is running, it'll actually take 1 Spark core, right? So what that means is, let's say you have a local cluster, let's say you have your own system and you want to run a Spark streaming job. In the Spark conf, you specify the number of nodes for your Spark cluster, right? So you'll say local of some number, right? So let's say you put a number 1 there. What happens is that 1 core will be used by a Spark streaming job. So you'll have no cores to process the data that is generated by Spark streaming. So you need to have at least 2 cores if you want to run Spark streaming and process data that is generated by Spark streaming. So this, yeah.
I don't know, you want to answer?
Yeah, sorry.
Just one, you have one statement saying that if you remember what it's one.
Mm-hmm.
And the comment for that statement is to make sure the data is not deleted by the time we query it interactively. Because the data coming every second, and we keep registered to the same table name.
Yeah.
And I try to understand the remember that statement actually remember. Is it to remember all the data flows through during that minute? Or?
Yeah, it'll remember the data that has flown through for the whole minute. Yeah. So you can query on the whole minute's data. There's another operation that you have that is, I think, reduced by window or something. What you can do is, we can get into the details. Maybe I'll talk to you.
So I think the next example is a little bit more complex, and the third example is much more complex. And I think some of the, so you can. So in fact, the most recent 6.1.6 actually has more interesting what are called stateful processing. So you can remember some projection of the history into a data structure and use that to actually take actions.
So what that means is, as an example, you could say have an average of some let's say counts received per minute, for instance. So that's a stateful variable, and you can remember that in Spark Stream.
Okay, so maybe I'll continue because the other 2 involve my personal credentials for Twitter, and it's a serious legal issue, right? You'll start seeing, because you can actually see quite a lot of information.
I just want to add one last thing. When you stop the Spark streaming context, it will also stop the Spark context itself. So that's where we have that, stop Spark context as false. Because if you stop it without giving this parameter on a Databricks account, it will stop the Spark context for your whole cluster, and you cannot run anything till you restart your cluster. So,
yeah.
Is that only the case on Databricks?
Sorry?
Is that only the case on Databricks?
On Databricks, you have to restart your cluster. On your own system, you have to restart your program. Otherwise, your Spark context is gone.
Okay, so I think that's sort of some working knowledge of streaming. So I see here that my UI user interface, I don't have any streaming running, so that's good. So here are a couple other pointers. These are just Databricks notebooks. We will do writing data to S3. So because there might be a project involving essentially mining tweets, filtering it, and then one project suggestion is to essentially follow Trump, Donald Trump, and he's generating a lot of tweets. So essentially following tweets that have Trump as a word or hashtags related to Trump, and then just trying to understand the graph of tweets around that Trump is generating, for example, right? There's interesting problems in social psychology and and political psychology that people are interested in, for example. So when you have situations like that, we cannot just keep writing to our Databricks, the distributed file system. We may need scalable storage like S3, right? So we'll go through the example of how to do this. So that's my sort of tweet collector. Right. So this basically captures live tweets. Right. So what I need to first do is load a whole bunch of packages I need. So the usual streaming stuff, but then there are Twitter specific ones, Twitter utils, and then some Twitter authentication imports. So then what I'm going to do is create a directory in the Databricks file system, which is our distributed file store, for storing tweets. Okay, so first we're going to store it in DBFS, in the cluster itself. So create a directory called raw tweets, right? And so I want to first make sure that there is nothing in raw tweets, okay, in case so it should be a clean directory. So now what I'm going to do is create this value called slide interval, and this is going to be sort of duration of 1 second, which is 1,000 milliseconds. Okay. So the slide interval is basically what I'm going to be sort of sliding along in the timeline and looking at all the tweets in that 1 second interval. So I'm going to create my D streams for this slide interval. Okay, so it's just a recall from before. Essentially, I'll have in every 1,000 millisecond interval, I will basically look at all the tweets, and I'm going to process them and store them. I mean, convert them to JSON. So to convert them to JSON, I'm going to use this Google JSON, right? Which is a Google library for JSON formatted text files. So now we're going to create a Spark context. So everything is sort of done a bit more boilerplate here. So SSC is my new streaming context. So its input argument is a Spark context and the slide interval itself. So before I go any further, right, this is extracting knowledge from tweets is actually easy, especially in Databricks. But there is a lot of legal issues you have to consider, okay? So I'm going to, let's, sort of point you to, this is just Twitter rules as a Twitter user. Right? So what are the rules you have to follow as a Twitter user? Just not as important as because what you need actually is the Twitter developer API credentials, right? So there is a lot of policy on what you can do with Twitter data, right? Because anybody can just see all the Twitter data. Okay, so please go through this, especially those who are interested in doing projects with Twitter, which I highly recommend because it's quite fun. But you just can't do stupid things like you cannot follow people. Okay? You cannot use the geospatial information of a user ID in a historical way to identify their whereabouts. And it kind of couples all the way down to the UN human rights, resolution. So it's a bit, and also the local jurisdictions apply. So if you're in New Zealand and operating from New Zealand, and then there are a lot of logical issues with interpretation of law as well. So that's, again, okay, it's complicated because if you are in New Zealand and you're looking at Twitter data in Saudi Arabia, I mean, I don't know how all of the laws actually apply. And I talked to a couple lawyers, and they actually are not sure. So anyway, we just have to be careful. For example, I cannot put the Twitter data publicly online and post it. The stuff I'm catching, I can't make it available for anyone to look at. Okay. Okay, so here's so what I've done here is I've hidden my actual credentials. So you need four big numbers. The consumer key, consumer secret, access token, and access token secret. You can actually get them by just going here and filling out some forms and saying, I agree, I agree. Okay. But I'm not going to unhide this because then you will see it by pausing the frame. So I'm just going to run it. Okay, so all my credentials are there. So I have an app called String Processor or something, and I'm just processing strings. Okay. So now, so let me just make sure that, yeah, so my user ID is this, which you can see, and my consumer key is this, but all the secret keys are not shown. Okay, so once I've done that, I've basically created my val called auth, which is all my credentials I need, done nicely through this configuration build thing, and then I have my val Twitter stream, which basically uses Twitter utils, and then it creates streams using the Spark streaming context and the authentication credentials I need. Okay, so easy peasy. We're suddenly having Twitter stream right there. Okay, so what I'm going to now do is this is going to come at you as just tweets, as text. I'm going to now create a closure here where every tweet is basically going to get converted to a JSON. I'm going to use Google's JSON to convert it to a JSON. And I'm going to essentially call that the Twitter stream JSON. Okay, so now I've done another transformation. So nothing's happened yet. Okay, so now what I'm going to do is I'm going to have a running count of the number of tweets collected so far. So I'm initializing that to be the long 0, so long integer 0. And then I'm going to create another val called partitions each interval. I'm going to call this 1. So this basically tells the number of partitions in each RDD of the discrete streams of tweets that are converted to JSON I'm going to have. So if by doing this, essentially what I'll be doing later on is repartitioning each RDD in my Twitter JSON file so that it has only one partition, which is nice if you want to write to one text file, right? It's one of the big advantages. Of course, that partition number will depend on what you're trying to do. If you have a huge interval, then you maybe want to partition it into a whole bunch of RDDs so that you can parallelize, take actions in parallel on each RDD that's coming at you in the D stream. But in this case, because I'm writing to a file, I want one file per interval, so that's what I'm doing. Now, what is going on here? Siva was saying that we have this for each RDD method. So I take my Twitter stream JSON, and for each RDD in this discrete stream, I have this double, which is RDD comma time, right? And I'm going to essentially transform it in this closure here. So first, I'm going to count by just rdd.count how many things are there, and if the count is greater than 0, that means there's at least one tweet. Then I'm going to have my val output RDD, which is going to be, this is what I'm repartitioning, you see. So RDD.repartition partitions each interval. So I want to repartition it so that I have exactly the number of partitions I want for each RDD. And then I'm going to take that and save as text file, okay? So save as text file just takes this raw tweets directory, okay? Which is what we created in the top level there, and then I'm just doing string concatenation to this subdirectory called tweets underscore, and then I'm adding it to the time.millisecond to string. So I now will nicely have my raw tweets convert to JSON, and for each block of time, which is a second, I'm going to have all my tweets in one file with this file name, okay? Tweets underscore the milliseconds of the time interval. And then I'm just incrementing the number of tweets collected with count, and it's all ready and set up. So all I have to do is start the Spark context, okay? So something should be going on. So let me go here, look at my UI for the cluster. And I suddenly see the streaming icon appear again. So I look here, and it should just be, see, as time is elapsing, I'm seeing the number of events per second, and that's just my flow. Some scheduling delay, processing time. So, okay. So I don't want to run this too long because, you know, so I have 1,781 tweets right now. 1,910. Okay. Let's collect. Okay, let's stop there. So I'm going to stop it, right? Because that's a lot of tweets, and I don't want to just run out of space. Okay, so now let me just make sure that my streaming is done. There should be no streaming in my UI. So, yep, so the stop worked, right? So I'm making sure I don't stop the Spark context while I'm stopping the Spark streaming context. Okay, so now, okay, this is if you're really paranoid, right? So, but it should be fine. It's just looping through. So now let me just look at this directory, right? Raw tweets was my directory where I dumped all the stuff, tweets for this millisecond interval start. So there's all these directories. So every second, beginning millisecond is the name of the file, name of the directory. So of course the sizes are 0, is just the directory name. So now let's, I have to do this properly now. So there's 14, 59, 39, and then what? 7688, 7689, 4 zeros, 3 zeros. Okay, so that's my file, because this is all fresh, live. So that's I'm just creating my tweets directory, just picking the second one there. And then I'm looking at what's inside that directory. So this is a usual distributed file system, sort of Hadoop. So you have this thing succeeded, and the file is part 000. And it's only 000 because I sort of turned it into one, you know, I repartitioned to have one partition. So there's only one file. So that's the. So there's a, you know, it has some content here. So now let me just count the number of tweets in that second, the 50 tweets in that second. Okay. So now what I'm going to do is use, the reason we turned it into a JSON is because data frames can automatically read JSON formatted file and turn them into a, you know, give us a data frame right out. So I'm using sqlcontext.read.json and this tweets directory, the file part 00, the file there. So that gives me out JSON as a Spark SQL data frame, and it's got a lot of fields here. Okay, it's quite a lot of fields. So that's what's in a typical tweet. Okay, there's a lot of information in a tweet. We'll sort of look at it in more detail. So here's the schema. So if I print the schema, so you can think of the JSON file as a sort of a tree, right? With various nodes in the tree, and each node is actually one of the fields, and it will have children along the tree with more features. So here's the root of the JSON tree, and then there is something called contributor IDs. It's an array that's nullable, and that has an element, which is a string. It has created at, which is the time that the tweet was created. Current user retweet ID. So if you retweeted it, it could be information about that. Extended media entities is another node, and that node actually is an array, and it's nullable, which means it may not exist or maybe null. And then it has element in it, okay? And that itself is a struct, and inside the element there is display URL and ID, for example, media URL, and so there's quite a lot of information. There's URL. If there's video, there's stuff about videos. And if you're interested in what is going on in terms of Twitter being used to wage wars, this is happening actually, ISIS is doing this. There's a lot of video images that are being transmitted. In fact, these guys are quite clever. They have this dawn of, glad tidings. There's actually a way to sort of fuse out Twitter's limits on how many tweets you can have so that they kind of bypass that and then use Twitter itself for, essentially sending videos to essentially frighten people that they're invading, right? That type of stuff. So in those cases, you'll probably go into the video content itself, maybe. Okay, so maybe you want to build an app that sort of filters out bad videos for your, I don't know, children or whatever. Okay, so there's a lot of information. There's latitude, longitude of the tweeter. If they enable that, that's usually the place. Some bounding box coordinates, latitude, longitude. So of course, not all Twitter users will allow their lat long to be public, but it's country code, and okay. It's got a lot of information. Okay, so what do we do with all of this? Okay, I'm just doing this just to show you a lot, right? So there's actually a lot of interesting papers being written by analyzing Twitter. In fact, the last 5 to 6 years has been a huge industry in it. So now what I'm going to do is just, because we have a data frame, I can just select the ID and the text. Text is actually the Twitter tweet content, I think. And we can just see, somebody said, this user ID said, just woke up. Okay, so whatever. So if it's not honest, true, and from the heart, don't do it. That's cool. So it's just 1 second, right? Kind of the planet, basically. Okay, I'm only showing the top 20 rows. So you can imagine a lot can be done with this kind of information, right? So one particular thing the social psychologists are possibly interested in is to actually build an appropriate, Twitter filtered pipeline. We'll see a filtered example soon. And then once you filter it and it's not too big, you can store it in S3 maybe, and then you can start, making sure that the filters are done so that the experiment you're designing with the filters and storing the tweets is the right amount of information to test various null hypotheses in social and political psychology right now. So a hot hypothesis to test would be whether Donald Trump is actually possibly, making the extremes, the extreme left and the extreme right, sort of diverge even further, right? That's, some pundits are talking that this is happening, but how do we actually test that? It's conceivable one can test that, right? Because all you really need is some way of parsing the tweets and maybe identifying various user IDs, using other information, and then looking for patterns of subgraphs. Because you can create a graph of tweets, who tweeted to who's arguing with who or whatever. So you can actually get some kind of a graph, and then you can color the graph based on the political affiliations of the candidates, which will involve a little bit extra work, because you have to probably cross-link Twitter IDs with like extremist websites from the Southern Poverty Law Center, for example, I shared some information on. And then you can kind of start looking at graph patterns, are there sort of, extreme, right and extreme left elements actually being sort of, how are these conversations proceeding from sort of Trump stream, whatever you want to call it. That'll be fun, right? That'll be really fun. If you can actually do that, and before the Republican primary, maybe you can publish in PNAS, but who knows? All right, maybe that's ambitious. So anyway, that's a good project, by the way, if anyone's interested. Okay, so now what we're going to do is write the tweets into a scalable commercial setting, right? This is S3. So once again, S3, AWS, because we have the AWS Educate grant, we have sort of some dough to write into S3. All of you do, right? So I can give you these credentials when your project gets to a stage where you really need to write to S3, not just put stuff in your DBFS. We have quite a lot of space already in the Databricks file system itself. But say you want to filter tweets for the, say, Trump stream or something like this, and you want to do that for 4 months, you definitely need S3, right? You're not going to be putting that in. And you may need 4 months of data to actually start seeing sort of time evolution of graphs of dialogues between different groups, for example. So that's this. And again, I'm not going to show you my credentials. Once again, it's because, if you want to use this, I want to make sure that you're aware of sort of legal issues with Twitter a little bit. But please come and see me. We can set this up for you. And then once I've done this, what I've basically said is, here's my AWS bucket name and mount name and my S3 file, which is my what I'm going to call it in S3. And then I'm going to mount this. So once I've mounted this, now what's in S3 in Amazon is going to be just like a local file for me now. So I can access things there. I can copy things, I can remove things, move things between there and my distributed file system here, my Databricks file system here. That's what we're going to do, right? So, so remember this dbutils.fs.help was the command that showed you all the things you could do with the file system. So first, I'm going to check what's in my mounted file system here. So I have my mount S3 data. This is what I mounted. So now what I'm going to do is copy recursively, right? Everything in my DBFS raw tweets. This is the stuff where I dumped all my tweets here. I'm going to sort of copy that into my raw tweets in S3. This is a directory I'm just creating in my mount. Okay. So this is going to take probably a minute, or, So it's going to take time, right? So you're moving data into S3. So alternatively, you can directly write to S3 as well. So in about a minute, that'll be done. So now all your files are actually in S3 at that point with so this is from a previous run. So then I'll just basically show me all the raw tweets in S3, and that'll give me all the files in S3 through my mount here. So then, well, I just wanted to remove the files because we have to pay for the file storage as well, right? So if you're not going to use it, you might as well remove it. You also pay a little bit for the bits being transferred as well. So, you have to think a little bit about how you're going to set up your experiment. If you're going to do a large social political experiment, you need to think about how you're going to store data. Okay, so that took about 59 seconds. So now just let's see what's there. Okay, so we're seeing all the new tweets that we gathered. It's already in S3. Okay, so I guess I'm going to just remove it just because I'm slightly paranoid. Because I told you we can't make tweets just public, so I just removed it. So now I'm basically just making sure, yeah. So there's nothing there, and yep. And then finally, I can unmount it, right? Because I'm done. This S3, I don't want to be sort of have it mounted now. And that's essentially how you sort of easy peasy, right? You collect tweets, put it locally, and then put it in S3. So the next example, okay, so let me just go back here and make sure there's no Spark streaming jobs running on my sandbox cluster here. Okay, good. So this example is slightly more complex. So now what we're going to do is, once again, look at the Twitter, these streams, and 1 second intervals again. But then now we're going to look at we're gonna have the slide interval of 1 second, but we're gonna have a window of 5 seconds into the past we're gonna look at. And for every second, we're gonna look at the past 5 seconds and then count the most popular hashtags over the last 5 seconds. and just report the top 10 of the most popular hashtags, okay? It's slightly more complicated set of operations, but that's interesting because then you can say what's the most popular top 10 hashtags in the last 5 seconds. Of course, you can change these windows and so on. Okay, so that's the idea here. Attach. So here's my, the same thing, sort of hidden away, my credentials. So now what I'm going to do is set up some, so this is a nice interactive way to ask users to change things. So I'm going to recompute the top hashtags every n second, every 1 second, okay? I'm going to compute the top hashtags for the last 5 seconds. So you can change these values and re-enter if you like, if you want to play around later. I'm going to wait this many seconds before stopping the streaming job. So these are sort of some parameters. I'm going to take those. So now I just want to make sure my output directory is clean. So I sort of start with the clean slate. So here's my creating function, right? This is like the first example, except now we're going to put all these little pieces of the Twitter job I showed you in the last example, all nicely in one nice function. This is just a hack of a Databricks notebook. So. Okay, so I have some var num and a var new context created just to set it to be false. And then I have this helper class called second value ordering, right? So I need this because I'm going to use this class to extend ordering, which is an existing class. And then I'm going to have a string and an int. So what I'm going to basically do is I'm going to have it compare the string and int by the second entry. So this allows me to order things by the second element in the two-tuple, so that I can use that to order hashtags by their popularity, which will be the count. Okay, so just a helper class. And then this is the function that creates the streaming context and sets up the Spark streaming jobs, right? This is our sort of creating func. So it's sort of taking your streaming context. Here's my new streaming context SSE inside. And then I have my authorization, my credentials, right? So this was from the previous instantiation. And then Twitter stream is going to be my create stream, just like in the previous example, with the SSE and my credentials. So next, what I'm going to do is parse the tweets and gather the hashtags, right? So I'm taking my Twitter stream, doing a map, there's a transformation, and this is underscore orientation, right? So every element is being mapped to its text by using the .getText method. Okay, after I've gotten the text, I'm doing a flat map, okay, where I'm taking the closure basically splits whatever comes in by white space, and then I'm filtering. Remember, this is again another transformation. So I'm filtering by anything that starts with hash, right? Because when tweets are seen as text, the hashtags begin with hash. So that's basically going to just keep the hashtags. So that's my hashtag stream. So from the hashtag stream, what can I do? I can do something more complex. So I want to compute the counts of each hashtag by a window, right? This is the 5-second window. So I'm going to do something reduce by key on a window of window length, right? So I'm going to basically have all these hashtags in the previous 5 seconds, and that's going to be my key, right? So after I've done the counts, so to do the counts, I'm basically going to be reducing by these hashtags in the previous window. So that's this function, reduce by key and window. So it's quite a nice construct. So what I'm doing here, I'm simply mapping the hashtag stream by the hashtag itself, whatever and then the integer 1. So each hashtag is initially counted as 1. And then now, instead of reduce by key, I'm doing reduce by key and window. And there, I basically, being explicit here, my closure contains this ordered pair, x and y, which are integers, and I'm returning the sum. Right? So that's basically the operation that's being done to the values that are associated with the same keys in that window. So this is where I specify my window length and my slide interval. Okay? So you can imagine this is very, very powerful. In fact, there is a very beautiful application of something along these lines for streaming k-means, where you have, remember the k-means algorithm took a cloud of points and found clusters, right? But suppose you actually have a streaming cloud of points, the points are moving around. Now, how do you do streaming k-means, right? Streaming k-means will find cluster centers dynamically as the stream is evolving, right? So that's actually a great project. While we're there, let's look at streaming k-means Databricks blog. There we go. So this is actually a good project for somebody who wants to do a nice, safe, and interesting project. So this is your sort of k-means clustering, right? This is iterative cluster finding heuristic, right? K-means. But now there's this notion of forgetfulness, and it's kind of a slight twist on this algorithm where now as the data is moving, the cluster centers will actually evolve. This is essentially streaming k-means. So anyway, there's notions of half-life and how much to remember from the past clustering and things like this. So it's a very powerful, non-parametric, unsupervised streaming clustering technique. Okay. So this is essentially some cluster centers and so on. So you should be able to figure out how to do streaming k-means by now, right? You've done k-means, and you've kind of have notions of streaming. The notebooks you can actually find. In fact, there should be probably some links to actual notebooks, or it should be available somewhere. So you'll have something to start off. And here is some example code. Let's see, let's check this out. All right, so you want to be able to start doing things like this because, the code is going to evolve and things will just change. And there's no way I can teach the same class again next year, right? So there's an example. So here's my actual, so this looks like the raw code itself. So there are probably, Sparks, ML streaming. I don't know what this one is. Let's check this out. Okay, so someone Freeman Lab. Oh, right. These are these neurobiologists, I think. They do some amazing stuff with streaming k-means because they're processing videos of like brain images of rats or something. And the initial step for data cleaning involves this, right? So, and this is massive, massive amount of computing because these are three-dimensional images of the rat's brain images, I believe. Okay. That was in Spark Summit 2015, 2014, was it? All right, so that's exactly how you could dive into a project that's interesting and okay, so now what are we going to do? So for each window, we calculate the top hashtags for that time period. And this is now I have my windowed hashtag count stream. So I'm going to take that and then do my for each RDD, right? So for each RDD in this discrete stream, that's already doing this reduce by key and window. I'm going to take my hashtag count RDD, and then here's my closure. Right? So what's happening in here, I'm taking the top endpoints. Top endpoints is just a value that takes the hashtag count RDD, and it looks at the top 10 values that top method is called. And then it's using the second value ordering, the helper function we passed in, right? So that its ordering is done by the second element in the two tuples of hashtag and the counts in the last 5 seconds. Now dbutils.fs.put is simply just putting the output directory, top hashtags. So the output directory is what we created, and I'm simply creating making a string called top hashtags and then putting the num, the variable num in there. Okay. So, and then I'm doing the top endpoints and making a string with the end of line character. So sort of there's a line break basically. And then I just do some prints and get out of here, and num keeps incrementing by 1. So I know which interval I'm in right now, starting with 0. The num was initialized at 0. So that's the first interval we're looking at. Okay, so let's evaluate this. So this is now all wrapped in a nice function. So it's a lot less boilerplate compared to the previous example. So now I'm going to create the streaming context. Okay, so I'm passing in my creating function I just defined into this. Okay, so nothing's happened, right? So now I'm going to go and start this. So I'm going to start the streaming context. And then I'm going to await termination or timeout with timeout job length, and then I'm going to stop it. Okay. So now if we go and look here, is it here? So there should be a streaming thing hopefully coming here. So we started the streaming job, see right here. So we click on it, it's showing me what's going on. So if I sort of refresh this, so my number of events per second is hovering between 40 and 60, and okay. So this would probably 57 seconds. So this job should automatically stop. Okay. And when it's done and it automatically stops, we can just view the results. So it'll basically be these files. This is from the previous run, and it has these names, and you can sort of, there will be 100 intervals. So hopefully 100 seconds is over already. Okay, done. So make some writes here, and then you shouldn't have to do this, but it's kind of there because sometimes there's strange behaviors I can't really understand yet. So yeah, so the streaming job is finished. There's nothing streaming, so you don't really have to run this. So now here's my DB utils. So I'm just listing the output directory, and as you see, we have these things, top hashtags 0 all the way through 99 and 100 is here. Okay, so it should be 100. So now I can ask, so let me just find something interesting. So this 10 has 305. So let me ask what's inside the 10th interval. So I heart awards is 5. So the most popular hashtag in the previous 5 seconds on the 10th interval is hashtag I heart awards. I love award. I don't know what that means. I don't know. Best fan army has been coming up a lot. Does anyone know what hash best fan army is? So anyway, so you can then, oh, there's a lot of Arabic ones here. But oh, it's interesting. Huh. Wow. So some bizarre thing happening here, right? Hmm. Yeah, so I don't know, that's a strange one, right? Because it's got hash, but then it's got a whole bunch of consecutive hashes, so I don't know why that's the case. Probably, yeah. something to investigate maybe. So yeah, the English ones are okay. So let's try, it's probably a parsing issue. Let's try 100. Okay, so here, yeah, so you see this looks like Korean. So there's again 2 hash, comma 2. So somehow this double, I don't know if Korean has double hashtags. Okay, so anyway, it looks mostly okay. Okay, so that's that. Oh, by the way, so next week is our sort of last week before the break, right? So Matt, Dominique, Shane, Andre is missing. So anyway, those who are sort of taking the course formally, we have to probably have a slight, maybe an informal chat, maybe in this early part of the course to figure out what you maybe are interested in. So if you want to think about what you maybe want to do for your project, just have a think about it so we can chat maybe 3 to 4 minutes each. You can say what your goals are, and what you're interested in maybe, and so I have a pretty rough idea of supporting you over the break maybe. Okay, so let me go through this guy. So this is the power plant pipeline, right? So let's open that worksheet and let me so anyway, normally I can open it and run all. So this will essentially do the first 4 steps. And remember, the only thing we want from there is that temporary table, right? The register temp table. So I believe it's already there. So let me just check if this power plant table is there. No such table. All right, good. So then I have to do something here. Ooh, that's strange. Oh yeah, okay. That's good. So I'm gonna have some strange behaviors here because there's some sort of, because this is the original sandbox cluster from the summer where we're sort of learning things, and it has some constraints on what it can do. So hopefully, okay, good. So we have the power plant table available for us, so we can continue. So let me have a sort of a backup line here. This is quite a serious worksheet. So let me go here. This is the one in the usual cloud you guys all have access to right now. But this worksheet is fully completed just a couple hours ago. So I might fall back to this because sometimes we have to wait for a few minutes for one of the huge cross-validation jobs to finish. So we may have to just come here. Let's see how it goes. So I'll go back to this cloud that nobody can come. Right, I'm doing this because of streaming context, Spark streaming context, only 1 per cluster. All right, so this is my vector assembler. Right? So I take my BAL called datasets, which essentially uses SQL context.table and converts this table back into a data frame. Now I use my vectorizer. So vectorizer uses this vector assembler to set the input columns and the output columns. So this is something we did before, and I'm going to kind of skip over all these display HTMLs that won't quite work here. So now I'm going to split the data into 20 and 80, right? 20% for testing and 80% for training. This is not the cross-validation, K-fold cross-validation. This is just splitting it into two pieces, right? Often we will do this when we're playing around with models and building intuition because this is a lot faster. And also when the models get too complex, we won't be able to do anything beyond this. Because K-fold cross-validation, as you will see, if K is 3, it will take the say 100 data points, that's your total data set, and it will create 3 pairs of sort of 1/3 and 2/3, okay, 3 randomized pairs. And then for each of that pair, it'll do this sort of testing and training and average over it. That's cross-validation, and that's expensive because of the multiple folds. Of course, in MLlib, all of this is done in a sort of parallelized way, right? So it's a lot faster, and it can scale nicely, but it still will be eventually costly. So this is just a little thing I said last time about limitations of deep linking the Scala docs. We just have to go to the right area in Scala docs and then do a search. Okay, so I'm going to cache these data sets just for performance, and we just saw this, so just taking some of just 3 elements out of this data set and the test set and the training set, and noticing that they're different. Now, here is the linear regression model. So a lot of you know linear regression already. Otherwise, you could have watched the videos that were linked in last week, right? So once I import the stuff I need for linear regression and the ML pipelines, I can create my val called LR. This is my new linear regression model, and then I can ask it to explain params. This gives me kind of what are all the default parameter settings, right? So I can control various things here. So for alpha equals 0, the penalty is an L2 penalty. For alpha equals 1, it's an L1 penalty. So that's basically lasso and ridge regression and extremes, I guess. Yeah, I really don't know. I know ElasticNet is another regularization method, but I don't know anything about it yet. So here's feature columns. So it's just by default called features. Are we going to fit intercept? Yes. And so on, right? The label column's default name is label. The max iterations, the number of iterations default is 100. So this is if the auto method down here, which is the optimization algorithm that will be decided automatically by Spark depending on the size of your data and all sorts of factors. If that goes via the gradient descent route or stochastic gradient descent option, then you need a control for the maximum number of iterations. Okay, so whether to standardize the training features is true, and so on. So here is now what we're going to basically do is set prediction column to be predicted power output, and then the label column to be PE. And then we have max iter 100. So this is where you can change the default parameters if you want. Okay. So I've now created my LR pipeline to be this new pipeline, and LR pipeline is now setting stages. And in the stages, it gives me all the little pieces that the pipeline is built out of through an array. And the array says, I'm going to use my vectorizer and my LR, linear regression model. So my LR model is basically now just the result of fitting this LR pipeline with the training set. Okay, so some LaTeX here for what this is. So the prediction Y is going to be a linear function of the features x1 through xk. Okay, so now I can find out what the intercept value was, again from last week, and what the weights are. So the weights are basically my coefficients B1, B2, B3, and B4. And Then this thing just allowed us to just filter out the things that are not power output. So this is the features, and it's just some hackery to put the weights, zip them with feature labels, and collect it, so we can actually see the weight associated with the feature, right? This is atmospheric temperature and so on. Relative humidity has this as the coefficient. And then this thing just basically orders them by highest weight to the lowest weight. So usually the larger the weight, that's an indication of the stronger effect of that particular feature. So and then just like in the picture, we noticed that atmospheric temperature had the highest negative correlation, and that's what's showing up with this large coefficient, as we discussed last time. And the others are sort of closer to zero, especially AP. So the effect is very little. So we can just sort of do this. Here's my linear regression equation, and this is essentially our little prediction system later on that we will do streaming on. So this is all just a recall. So now I'm basically creating, I'm basically transforming, I'm calling the model that's been fit, and then I'm applying this dot transform method and putting the test set in. So the test set will get automatically applied to the model, and then it'll do the predictions and the predicted PEs. So we're now able to see that although we did not let the model see the test set and only the training set, it's predicting pretty reasonably well. So that's that. And then, so now we wanted to look at the metrics. So in fact, we take various regression metrics to quantify how good the fit is. So here, for example, sort of added an extra okay, maybe it's sorry, so I think it's here. Week 5. So this one basically is where we tried to stop last time. So I believe, there we go. So, because I was confused about, exactly what R square was and the explained variances and so on. So, so here are all the formulae for R square is whatever. Residual sum of squares divided by the total sum of squares and so on. So you can get back at that. So let's go back. So remember, this one just stops before deployment. So week 6 basically continues from there again. So. Okay, so let me just move this here. Come back to this one. It's live. So once I've made my metrics, I'm going to basically say my root mean square is RMSE and my explained variance and so on. So I'm able to, I'll just see them all in one. So the question is, can we improve the root mean square error beyond 4.6, maybe slightly smaller, closer to 3, for example? So here's my display of the predictions table. So I'm just seeing the full thing, so vectors and predicted PE and PE. Right. So now I'm calculating the within RMSE, basically. So this is going to be a nice way to see how good the fit is. So I look at my PE, predicted PE, residual error, and within root mean square error. And all of this is done nicely via data frames. And then I can look at my distribution of within RMSE, histogram of within RMSE. So then there was a bug here before, I think. So then, the question is what fraction of it is within 1 RMSE or 2? And if it's around 97 or 98%, then it's a pretty decent model. That's what this pie chart is calculating, right? So there's select case when within RMSE is less than 1 and within RMSE is greater than -1, then coded as 1. When within RMSE is less than 2 and -2, then coded as 2, else 3. And this is the end of that case statement. And then I'm calling that as RMSE multiple. And then I'm doing a count from this table with the same group by statements later. Right? So that's basically catching what fraction of errors are within 2 and 1 with mean square error. Okay, so now the tuning and evaluation was to see, that's just one particular default value. So can we improve this by playing around with different hyperparameters? That's what this, this process is, step 7. And so now what I'm going to do is create something called a regression evaluator. So the regression evaluator basically needs a label column, which is my predicted power, my power output, and then it has a set prediction column, which is the predicted PE, and then it has a metric, which is RMSE. So once I have an evaluator, then I need an estimator. So with an estimator and an evaluator, I can define a so-called cross-validator, right? So I'm having a val called cross-val, and it's a new cross-validator. And cross-val's estimator is set to be this LR pipeline, which is what we've been doing for our estimator or model. And then cross-val.set num-folds is 3. I'm doing 3-fold cross-validation. And then I'm doing my evaluator to be the reg eval that I just defined earlier, right here. So I think that's basically the main things for a cross-validator. So cross-validator also requires a set of estimator param maps. So this is a map of parameters on which to test the model, right? To see which particular value or hyperparameter is good. So for that, we're just basically taking this reg param to be an array from 1 to 10 and dividing by 100. So we get an array from 0.01 to 0.1. This is your regularization parameter sort of interpolated between L1 and L2 regularization errors. Okay, so now we can sort of chase this here for more details. Now I'm going to create my param grid. So the param grid basically takes my param grid builder, adds a grid, builds it, and once I have my param grid, I'm basically ready to go. And this is my cross-validation model. So I'm fitting the training set to my cross-validator, and that gives me my CD model. Okay, so I already mentioned this to you. So cross-validator is one way to go. The other way is just splitting it into validation and training set just once. Right? So that's the other way to do model tuning. So now let's just see how well this compares. So this is our sort of best tuned model out of those 10 different regularization parameter values. And let's see, the RMSE is not that much different, right? It's still around 4 something. So we haven't really improved the model by tuning it, at least on this parameter, right? So the initial untuned model was pretty good, right? It's probably because the data itself is like, there's only one very strong correlation, maybe, it's not, you can't do much more with multiple linear regression. So then the idea was to use decision trees. So we've seen decision trees in 2 weeks ago. So So this is essentially rerunning that through this through pipeline. So this is your decision tree pipeline DT. But now we're going to use the decision tree for regression, not decision tree for classification, right? Because now the difference is the label is a real value. So when I'm sort of chopping my feature space according to, so I choose the best dimension and the best place to chop, again, according to some heuristic, right? So instead of the impurity measure that sort of looks at how many red and black, it's a binary case, are inside each cell and choosing the purest split. Now I'm going to basically look at the mean value of all the labels, right? So I have some power output for a given partition of the feature space, and I just take all the power outputs in that cell and then find the mean of it. So my response is going to be the mean value. So I have to make sure that my that I'm partitioning it such that things that are sort of closer together in the mean value are grouped together. So that's the heuristic for regression. Okay, so same idea basically, and it's also a greedy search because you're at some given partition and then you decide to chop on a box. Then you go through all possible 4 dimensions here. There are 4 features here, and for each one you find the optimal split and do it in this greedy way. Okay, so I'm setting various parameters, max bins, and feature columns, predicted columns, and so on. So, and I'm again applying things that I've built before. This is a nice thing. So I'm recycling parts of the pipeline for linear regression with decision trees, like the vectorizer, for example. Okay, so and then I can just use the same sort of cross-val set estimator to be the DT pipeline now. And now, but my parameter grid builder is different. I'm going to have a grid over just depth 2, max depth 2, and max depth 3, for example. Right? This is a tree, so I've got a couple of them. You can increase it if you really want. So then cross-val set estimator param maps is grid param maps. So now the cross-val is ready to go because it's got an estimator, an evaluator, and a parameter map. Now DT model, I'm fitting it. This is going to take a little bit of time. Oh yeah, this one's fast. The next one will take a bit of time. So then I do DT model, test model as instance of pipe. What's going on to debug string? Pipeline model. What am I doing? I'm on 1.6, I think.
What statements did you run?
Oh, did I skip something? No, did this. Did I? So anyway, I've been kind of moving the notebooks back and forth between clusters, and so there could be some, okay. Let me try this one. This should work. This could be
Pipeline model and decision tree regression model are not important.
okay. Oh, this one. No. Oh, right.
Doesn't really matter what you do, you can just do it in Excel right now.
Okay. Do that. So let me actually cut through, right? This won't finish anyway because the training of the gradient boosted regression tree on the ensemble is actually like 7 minutes. So I'm going to just jump into this and we'll continue so you get the ideas. So what basically happens is you sort of find out that the tree is pretty good, but it's not all that great, right? So so you're doing this sort of best model across depth 2 and depth 3, and then you find out this is essentially the splits and the splitting values and so on, and it's okay, but it's not it's not spectacular. So then what we're doing is here's the comparison with the metrics, and we find that the root mean square error didn't really improve. And so what to do next? So then the idea is to go through gradient boosted regression trees, which are an ensemble method. So for this class, those who know this. Those who want to know it at a high level, just look at this add a boost thing. So essentially, you're going to have a whole lot of trees, and each tree is fit separately, and then you're going to take the consensus of the average of all the trees. That's the idea, and these are very, very nice methods. And once again, there's the link to the gradient boosted trees. So when you run this, I'm not going to run this, but it'll take a little bit of time. You can essentially do the GTB regressor and set the seeds and so on. Max bins is another parameter, and the maximum iterations is 120, so that's going to train 120 trees, okay? And I once again have my pipeline, grid parameters, and I'm playing with just 2 depths. And I'm doing cross-val fit. So all of this, it'll take 291 seconds, I guess. And then when that is done, you can find out how well it fit. So the RMSE is a little bit less now, 3.8 instead of 4 point something, 5 point something. So that's good. So then we say, okay, let's call it good. And here is essentially the debug string for that, for the GBT model. And we conclude, okay, so this is our best. So now what do we do? So come to deployment. So everything should work if only one person is running it, and there's no multiple streaming context. So I take my final model to be the GBT best model, right? So this will be the best model that we've done. And then I'm essentially creating a table for predictions here, okay? So then what I've done is this whole streaming job is set up, right? So there's a whole bunch of imports, and I'm going to set up my streaming pipeline for people querying, okay, here's my atmospheric conditions, what should be the power output? And I want to answer that. That's what I'm going to do. So this is very similar. It has a notion of a synchronized queue now, and that's a slightly different thing than the other 3 streaming examples we saw. And I also have this creating func, which is same name as the previous examples. And I'm creating a streaming context. I have a batch interval and D streams. And so what I'm doing now is when I'm using the final model to transform a JSON message. So the message comes to me in this JSON string. Here is my sort of feature values. What should be the prediction, right? So I'm going to take that JSON message and use my final model that I've done and use the transform method, because the transform method, all it does is it takes some new values and does the prediction based on that model. So that's exactly what I'm going to do. And when I've done that, I'm going to turn it into a data frame, okay? And of that data frame, I'm only selecting these columns, AT, the features, and the predicted value. Okay? And then I'm writing that to in append mode, I'm writing it to power plant predictions, okay, and saving it as a table. Okay, so that's essentially what's going on here. And then I'm starting my Spark streaming context. And if I do ssc.start, this is what will happen. And I'm just now, for example, if I have my queue, and I add to my queue RDD, which is made up of a sequence of strings, where this AT value is 10.82. So this is like your JSON request that's coming to you. And then what I can do is do the prediction for it, and it'll be updated in this table. So you can sort of look at this table, and here's my input that I gave it, and here's the prediction that the final model was applied or transformed using this JSON string that came in, and that's essentially in this table. And then here's a new measurement that's coming in, and then once again, that gets processed, and here's my SQL. This table gets augmented with an extra row now, which is the new predictions, 10, 40,000, whatever. So for that, it's predicting like this. And then the last cell basically says, are the predictions very close to the real data point? So we're just going back to the power line table, the original table, and we're simply looking at for AT, should probably be capital AT, but doesn't matter. Okay, and AP value between this, because we're sort of trying to find out if for these query features, what is the actual values in the original table, and it looks very reasonable. It looks very reasonable to what the final model predicted, right? So it's around 470-ish. So it's just a little sanity check, and then we just stop the context and some references. So the idea is that this is kind of a silly example, and it's a huge one, but it's showing all the pieces of the pipeline, right? So that's what a data scientist or an applied data scientist will be, will be doing, right? And engineers can make this much better and more efficient and so on, but the full pipeline is there. Data, cross-validation, you tune, you deploy, right? So you model, you tune, you evaluate, make sure it's decent, and then you deploy. So that's the end of the show for this week. Are there any questions? So, I mean, you're interested in robotics, right? So in robotics, it's going to be much more complex. So you have multiple robots, and I don't know, each robot will have a location, and maybe they have to coordinate their efforts, and maybe those decisions can be done in the cloud using a different machine learning model, regression. And then maybe the decisions can be served to them, and the one can work on the timings as well, like how quickly the robot needs some kind of intelligence from the cloud, so there's issues there.